So in the last video we defined this subdivision map. And we proved that it was a chain map. Now what I want to prove is that subdivision is chain homotopic to the identity. And let's recall what that means. There are homomorphisms, sigma from Cnx to Cn plus 1x. D sigma plus sigma d is equal to u minus the subdivision of u. Okay, so it's identity minus d sigma plus sigma d is the identity minus the subdivision map. Okay. So we're going to define, so as with the definition of subdivision, so in order to set up subdivision, we basically just had to define these theta n's, where theta n was the subdivision of the identity chain on delta n. Similarly, here we just need to work out what sigma is going to be on the identity chain and then propagate that. So we're going to define these maps to kappa n, so that's going to be in Cn plus 1 delta n, in kappa prime n, in Cn delta n. So kappa 0 is just going to be 0, and then kappa n is going to be the identity chain minus the subdivided identity chain. That was equal to, that was what we were calling theta n, but actually let's just call it the subdivision identity here, minus the sum from I is 0 up to n minus 1 to the power I delta I hash of kappa n minus 1. So this was kappa n kappa n prime. Okay, so this is going to be an n chain in delta n. You know, the identity is an n chain, subdivided identity is the n chain. These kappa n minus 1s, they're going to be, they were in Cn of delta n minus 1, so we push them forward. This is all happening in Cn. And then kappa n is going to be beta of kappa n prime. And then remember, this was the operational linear chains, which just inserts the barycenter. Okay, so that gives us our kappa n's, and then we define. Okay, so we've got some basic simplex. You map u from delta n to x, and we're going to put sigma of u. We just take u hash of kappa n. Remember, see, this u hash is giving me u as a map from n, delta n to x, so it gives me a map from Cn plus 1 delta n to Cn plus 1x. Okay, and we apply that to our basic kappa n, and that gives us our sigma of u. Okay, so that's the definition. We need to check it works. Okay, so our claim is that that's what we're supposed to be claiming, that d sigma plus sigma d is on u is u minus the subdivision of u. So let's firstly do the case where n is 0, well, kappa 0 is 0. That means that sigma of u is just 0 in that case. And remember the way subdivision was defined. Subdivision of a zero chain is just equal to itself. And so this equation that we're looking at here is just saying 0 equals 0, which is true. Okay. And we're going to claim that we're going to assume inductively that this identity holds for all n-1 chains in all spaces. So we'll apply it in the case of the boundary of iota n. Okay, so then in that case we know that dv is just d squared iota n, which is 0. And so so what we get here is that the boundary of sigma of v and then in principle there's another term here, but we don't worry about that. And then you've got this term here is just 0 because dv is 0, and then here on the right hand side you get d iota n minus the subdivision of d iota n. But we know that subdivision is a chain map, so this is the boundary of iota n minus the subdivision of iota n. Yeah. So what's this sigma of d iota n here? That's the subdivision of the sum from I is 0 to n minus 1 to the I delta I. So this is this is the sum from minus 1 to the I. Then you get you're subdividing this, so here you just get delta I hash of kappa n minus 1. Okay, this is how we subdivide delta I. You apply delta I hash to the appropriate kappa. Delta I is an n minus 1 chain, so we apply delta I hash kappa n minus 1 to get this here. So this is kind of minus the last term in kappa n prime. Okay. So here you've got a minus sign, it's plus sign. Okay. So this time here you've got on the left hand side here the sigma. You've got the boundary of sigma delta iota n, which is this last term here, and then you've got iota n minus sub. So we put all this together. What this is telling us is that the boundary of kappa n prime is 0. Okay. So now let's recall that d of beta of kappa n prime plus beta of d of kappa n prime is kappa n prime. Okay, and now we know that the boundary kappa n prime is 0, so that's 0. And then beta kappa n prime is kappa n. So we find that the boundary of kappa n is kappa n prime. So that's going to be a key ingredient. Okay, so we learned that d kappa n is kappa n prime. Let's just record that up there. Okay, so now let's look at d sigma u. That's d of u hash of kappa n. But we know that u hash is a chain map, so this is u hash d of kappa n. That's u hash of kappa n prime by this thing that we just worked out. Okay, so let's recall definition here of u hash. So we got u hash, definition of kappa n, so we got u hash of iota n minus u hash of sd of iota n minus the sum minus 1 to the I, then u hash delta I hash, so that's u composed of delta I hash of kappa n minus 1. And so here I've got u hash of iota n, let's just apply, iota n was just the identity map, we compose it with u, I just get u. Then here, u hash of, remember u hash commutes with subdivision, that's subdivision is natural, so this is the same thing as subdivision of u hash iota n, which is the subdivision of u. Minus, and then what's this here? This is just the subdivision. Sorry, this is sigma of the sum minus 1 to the I u composed delta I. Because applying sigma is just acting on this kappa n minus 1. So we sit for n minus 1 chains, that is. This is an n minus 1 chain, so this is just the same thing as sigma of that. Okay, which is u minus sdu minus sigma, and then this thing here is just the boundary of u. And then if we just rearrange this, bring this term over that side there, you get d sigma u plus sigma du is equal to u minus the subdivision of u. Okay, so now we've shown that we've got a chain map, we've got a chain homotopy between the identity and subdivision. So that means that subdivision acts as the identity on homology groups.